one steel tables, that 530 UB, that we need to take it. So 530 UB, 513 UB, and what was the let's close this one. Let's close this one. Okay, there you go, the first one. Let's close this one. Okay, the first one here. So now we have this 530 UB 92. So for that 530 UB 92, 530 UB 92, we have 530 UB 92.4. So you have day 532, width is 209, and thickness of the flange 15.6. So 209 and 15.6. 209 and 15.6. That's the dimensions. And then you have this 10.2, that is the thickness here for the web. So if you want to calculate this distance from here B over T, you have 209 divided by 2 over 10 divided by 2, you get 99.4. I hope you understand that. And thickness is given 15.6. Now this Fy, you can take this Fy from the next page. Fy from next page. 530 UB, you have flange 300, and if you want to take it web, you have 320s. Okay, but if you want to take it minimum for both, that's still okay. As I mentioned, different cooling rate are applied in here, because when you temperature and when you cool it down, they have a different stresses because of the different yield strength, because of the different thickness. So that's the yield strength, 530 megapascals. Now lambda E, that equations given in our standards, close 5.2.2. I can show it to you here, that plate element slenderness lambda E equal to B on T square root Fy on 250. So that equation is written here, 99.4 and 15.6, that is given thickness. B is 99.4. By the way, these values, that 99.4 over 15.6, also given in our one steel table. I can show it to you here. So if you go back here and if you just take it this one, this is your B on T, which is 6.37 here. So you if you like, you can put 6.37 straight away here. You can put 6.37 straight away here. And then 300 over 250, you have 7 as an element slenderness. Now we need to find two values, which is the plasticity limit and the yield limit. This is plasticity limit, and that is yield limit given in table 5.2. So if you come back here, that first row, plate element is flat, longitudinal axis is supported. One edge, I can show it to you here again, that if you have these beams here, then you have, this is the flange, this one is flange, this one is web. So this flange is longitudinal, one edge is supported, as you can see, this one edge is supported. That's what it says, flat, longitudinal, one edge is supported, uniform compressions, because when you do this bending, this edge goes in the compression. So that is compressions. And all our universal beam, as I mentioned in my workshops, all our beams are hot rolls. All our universal beam are hot rolls. So HR is your hot rolls. It's written here, hot rolls or hot finish. And for HR, your plasticity limit for the flange is 9 and the yield limit is 16. That you can grab it from these tables. So 9 and 16. So I hope you're okay with that one. 9 and 16. So if you take a ratio of lambda E over lambda EY, which is 7 divided by 16, you get 0.4. Now we do the same thing for web. Same thing for web, meaning you can have this B on T ratio, and that is your web, that is your B, that is from this corner to this is B, and this is your thickness. So that's, you can find it out from our one steel tables as well. So let's say B is 533, so there's this distance, so this total distance is 533 millimeters. That is coming from one steel table, by the way. 533 is coming from here. 533 is coming from here. Now once you have this 533 depth, and thickness is also given here. Thickness of the web is 10.2. So all the dimensions are given here. Okay, so we have this B which is 501.2, thickness 10.2, given in one steel table. Fy is 320 for web. Where it is, I can show it to you here. If you go on the next page, you have this 320 megapascals. That's for the web. So you can take it at 513. I think in our lectures we take it minimum, but if you want to have more accurate one, you can do it. Each element has a separate one. So, and if you use 300, still not a big issue. So that is 55.6. That is lambda E value. Please note this 501.8 over 10.2 also given in our one steel tables. If I like you to show you that this D on T ratio is 49.2, so you can use straight away 49.2 here. You can straight away use 49.2 here. This 49.2 straight away. 320 over 250, you get 55.6. Again, you can get the plasticity limit and yield limit. You can use this one. So over here we use this one row. I think this is the web, where you have flat plate, both longitudinal edge is supported. You can see this edge is supported, this edge is supported. This is the web, and both edge are supported. So you have both heads supported. Compression at one end. So if I bend it, there is a compression here, tension here. So that is good, and you don't need to classify which one is this in here web. So you have straight away 82 and 115. So you have 82 and 115. And again, you take this ratio lambda E over lambda EY, which is 55.6 over 115. That's we calculated 50.6, 115. You get 0.484. So get a ratio lambda E, then lambda S equal to 55.6. So which one is greater? You can see 0.484 is greater and 0.436 is not. So we need to have web is a critical one. So we take lambda S equal to 55.6. Lambda SP is lambda EP 82. That is coming from here 50.6 and 82. Since lambda S is less than lambda SP, then section is compact. Where is written? Here you go. Compact section. When your lambda S is less than lambda SP, then your sections is classified as a compact. And that's what the question is asking us to do. That tell us whether prove it whether the section is compact or not. And we prove it that because our lambda S value, that is for our web, because web is the highest ratio. So say that web has a lambda S value of 55.6 and lambda SP value of 82. So 55 less than 82, then section is compact. Now if the section is compact, then we can calculate this. If you remember yesterday we work on this plasticity elastic modulus, which is effective section modulus. If you want to calculate the effective section modulus ZE, which is lesser of, this is plastic section modulus, or 1.5 of elastic section modulus. So you need to get these details for ZE. So that ZE is given here, that minimum of S or 1.5 Z. Now S is your plastic section modulus 2370. Where is that? If you go back here and S value welded column, universal column. So we are bending about X axis, strong axis, and S value is plastic section modulus 2370. Don't forget to multiply 10 to the power 3, and elastic modulus is 2080 times 10 to the power 3. So that is taken here. Minimum of plastic section modulus or 1.5 times elastic section modulus. If you multiply, that would be your minimum 2370. So that is your ZE. So if you want to calculate the section capacity, this equation is given in the standards. MS equal to Fy times ZE. We already find the ZE value from here for compact sections. And yield strength, we have two yield strength. If you remember, we have two yield strengths. Now here you need to take the minimum yield strength. Okay. Why we take the minimum? Because that will also give you the critical strength. We don't want to overestimate our capacity. So in here you have two values. I told you on my lectures why you have two values, because different cooling rates and different thickness. So you have 300 and 320. Always take a minimum. So for that case, we take a minimum of 300 and 2370. That's ZE value. So you have 711 kilonewton. You will get the big number, but you need to divide by 1000 and times by 1000 again to convert into kilonewton meters. And then you need to multiply by capacity factor 0.9. Where is the capacity factors? By the way, if you go back to the all the way to the front, you will get the capacity factor. Let me find the capacity factors. There you go. Table number 3.4 has a capacity factors. Members subjected to the bending, regardless of any, you have all 0.9. So we have a capacity reduction factors 0.9. Is basically reduce your capacity by 10%. Why? Because there is some uncertainty in our calculations, some assumptions and so on. So to take into account that uncertainty, whatever you get, you just multiply by 0.9. So this is like a safety factors, you can say. So that is the one. After confirming that section is compact, same like before, determining the design moment capacity of the welded beam, bend about is strong concrete, and is exactly the same. Only the difference is now here you have 1000 welded beam, 215, exactly the same. There is not much difference between the one and second one. So but for the completeness of the workshop, let's go through with you that you have 100 WB 215. Where it's gonna helpful? You need to go to the welded beam, because WB stand for welded beam. Universal beam and the welded beam, welded columns and welded beams. Now let's remove all these details from our lectures yesterday. So what was that? Thousands welded beam, and what was the designation for the weight? 215, please. So that is go here, and that is 215. So we're going to use 1000 D. Width is 300, thickness is 20 flange, wave thickness is 16, and that's it. So if you like to know more designations, that all the designation, the symbols are given here as well. So let's use this one. I think you know the drill now. We need to do the flange first, and then we do the wave. And for the flange, we're going to calculate lambda E, and then we're going to get the lambda EP and lambda EY, and then I think we do lambda E over lambda EY. There's 3 steps we're going to do it. Step number 1, we're going to get lambda E. Step number 2, we're going to get these 2 values from the table, plasticity limit and the yield limit. And the step number 3, we just take the ratio, and then we finish with the flange. For the wave, we do it again. We take the lambda E equations and we plug the value for wave. And then we come back here and we take this plasticity limit 82 for weight, yield limit is 115. Again lambda E over these values and we take the ratio and we check which ratio is bigger, and then we will just going to work on that one whether it's compact on or not, because we need to show that lambda S, because we have two lambda E, because you will have a lambda E for whip, lambda E for flange. Now which one lambda you going to take it? That because lambda S equal to lambda E, but you have two lambda E value. So the ratio between the lambda E and lambda E, whoever the bigger one, that's going to take the lambda S, and lambda SP would be equal to lambda EP if it is the wave or flange. Okay, so that's, and then we will show that this one, and once it's done this one, we will multiply Fy times ZE with the capacity factors and so on. So that's the overall procedures that we're going to follow. Let me show you that. So again we do B over T. We have these equations, B on T, B on T. So lambda E is equal to B on T square root Fy on 250. Right, that equations I can show it to you here again. That is called plate element slenderness, B on T square root 250 on square root Fy on 250. Now that value that you will get it is this one, outstand. We call it outstand. So this is your B, and I hope by now how you going to calculate this B, like 300. This is 300 divide by 2. Take away this is 16 divide by 2, so you get 142 millimeters. That is your B. Thickness 20 is given in our one steel tables 20. So B on T ratio, you take it 142 over 20, and if you like to confirm it, the one steel tables give you that B on T ratio for the, this is basically B on T ratio for the flange, and this is your B on T ratio for weight. So you can confirm it that 7.10 is the value that you can use it. 142. So if you do 142 over 20, it will give you 7.1 or something. Right, so that is confirmed. And then 300, the yield strength that you can get it from the next page. For 1000 WB 25, 1000 WB 25, you have 300 and 300 for both. So that's our life is easy. For wave and for both wave and flange, you have 300 megapascals. So we just plug that 300 here, we get 7.8. Now you have lambda EP and lambda EY from the tables. I think you know the drill now, that this first row is representing your uniform compression. One longitudinal edge is supported. This is your flange. One longitudinal edge supported, another one is not supported, and this is the welded beam. So I think heavily welded longitudinally, because it has a heavily welded longitudinally. So I think HW, and we will take 8 and 14. Plasticity limit 8, yield limit 14. So that is 8 and 14 for the flange. And you just take lambda E over lambda EY, you get 0.555. We follow the same strategy, that lambda E equal to B on T square root Fy on 250. This B on T ratio we can get it from here straight away. Now this first page you can get it from here 60, or if you want to calculate, you can calculate as well. So that is 60. So you can have this, you can put this one as a 60 here, or if you want to calculate, you can do so by finding this distance, that is your B and that is your T. So you have 60, 300 megapascals. I show you that yield strength is 300 over 250, you get 65.7. Now lambda EP for flange and lambda EY for the web. So if you come back here on almost four these lines for any residual stress, you have 82 and 115. Why I use this one? Because it's a flat plate. Yeah, it is a flat plate. It has both longitudinal edge supported. This longitudinal edge, the flat plate. This edge is supported. This edge is supported. Compression in one end. Yeah, it is compression in one end, tension in the another end. So that's what you have 82 and 115. So you got 82 and 115. So we do 65.7 divided by 115. So you have 0.571 as a this one. Since the wave has the greatest ratio, so you can see the wave, which is you're going to take the ratio 0.571 and 0.571. Who is the winner? Wave is winner. Winner is meaning that they are the critical one. They will buckle. They are the weakest point in the beam. So greatest ratio on this one. Then lambda S is lambda E is equal to 65.7. That is your lambda S, because standards wants you to know lambda S value. And for that lambda S value, you have two value, lambda E for flange and lambda EY for web. Now, which one you should take? The ratio that you're going to get it between this is largest, so that's that ratio. So lambda S, the wave is the largest, so lambda S equal to lambda E of the wave. So that's 65.7. That is done. Lambda SP, because we also need this lambda SP. Now SP is for wave, which is the plasticity limit, and that for wave is 82. So we take it 82. There 82, and this is 65.7 less than 82, because standards wants you to know that lambda SP is less than lambda S is less than lambda SP. Then your section is compact. So we take effective section modulus ZE. Then we calculate effective section modulus ZE equal to minimum of plastic section modulus, or you have a 1.5 times elastic section modulus. And in the lectures, I have given the full definition of plastic section modulus and elastic section modulus. So we have a compact, we prove it. Right? It says that, can you please prove it? So we said, okay, yes, we prove it. And then we need to calculate a design moment capacity. Now to calculate a design moment capacity, which is MS, denoted by MS, equal to Fy on Ze, which is the yield strength times the effective section modulus. And that effective section modulus for compact, please note you have different effective section modulus depending on whether you have compact section, non-compact sections, or the slender section. So for compact sections, we can calculate effective section modulus by taking the minimum of S and 1.5 Z. So for that, minimum of S and 1.5 Z, S is 9570. If you take it here, welded beam, this one, S value is 9570 times 10 to the power 3, which is your plastic section modulus. This is your elastic section modulus, and it is 8120. So if you just do the quick calculations, that would be the minimum one would be your plastic section modulus. So therefore 9570 is taken here. Sorry. 300 and ZE value is 9570. That is your plastic section modulus 10 to the power 3. You get 2871. Again, you multiply by the capacity reduction factors, and I show you that capacity reduction factors. I can show you again that capacity reduction factors was table 3.1. For bending, you have 0.9. That's just the safety factors. Whatever your calculations give you, you just multiply by 0.9, which is reducing by 10%. So your final value is 2584 kilonewton meters. Right, so I think there are two examples where we prove it whether it is the compact sections or not, and then we will calculate the design moment capacity. Now let's do the third one, that beam has a span of 6 meters simply supported beam. So you have like a beam and you have this UDL load and it is 6 meters. Okay. Has full lateral restraints. It supports a total service uniformly dead load. Dead load is given 24 kilonewtons, not including the own weight, and central concentrate service dead and live load. So there is some center 40 kilonewton and 100 kilonewton center load. Determining the most economical universal beam section, consider only flexure. Do not consider shear and bearing. What is the maximum spacing of restraint to ensure the full restraint of the beam? So what they want, they tell us that, can you please tell us the universal beam that you want to take into account? He says that, okay, you go here. Someone might say, look, you might look the if you go from down to up. If you go from this down to up, its capacity will be increased, right? That's what it says. You can pick 610, 125 UB and it will have a highest moment capacity. But it's not economical. You need to check how much moment do you need to carry, and you need to select whether this, which one is more economical. Okay, so that's how the engineers wants to reduce their cost. So let's work it out for that. So what we're going to do it, that we're going to calculate the bending moment. We will calculate the design bending moments. Let's say bending moment diagram, M stars, and for that M stars, we're going to, let's say M star equal to Fy times Zi with 5, and then we will bring these 5 across, Fy across, and we're going to calculate Ze, required section, required Ze, and then we go back in the table. We go back in the tables, and we're going to find the closest, our plastic section modulus. We're going to find the plastic section modulus which is closest to find our beam. So that's the overall procedures. So first steps, we need to take into account couple of things. Like we need to know, when someone asks you, can you tell me the universal beam, you need to know these values. M stars you need to know. I think the capacity factor is 0.9 for bending, and then you need to know Fy. Typically it is 300 megapascals. So and then you can calculate Ze. From that Ze you can see which S value, the plastic section modulus, that you need to know. That's we can quickly do it. Okay, so these details here, I'm not going to go through this one. Here is just calculating your bending moments. If you go back and check all your mechanics of solid knowledge, structure analysis and all, you can calculate this bending moment for me. This 80.4 and 150 kilonewtons, because generally we will give you this bending moment in the test, so you no need to worry about it. This is just for you to understand the stories. So let's say you have calculated the maximum bending moment 322 kilonewton meters somehow for this dead load, live load, and you put this UDL and you put this bending moment. So let's say you have a bending moment 322 kilonewton meters. So we need to know which beam that will have a capacity more than 322 kilonewton meters, right? Because we don't want to fail our beam. The beam will subject to 322 kilonewton meters load, and when the beam comes to the 322 kilonewton per meter, it should be have a capacity more than 322, so it can safely carry the load. So you know that 5 ms should be greater than whatever your demand, and the capacity factor is 0.9. And if you just wants to know ms, then you will just divide by 0.9. Your ms value is 357. By the way, ms is here. ms is here, and the condition is here. Your capacity of your beam should be greater than your design moment. So this is the capacity, designs bending capacity of your section should be greater than your bending moment or your demand. So you have this ms value, which is 357, because you can calculate ms, right? Because you have m star, which is 322. You get it from bending moment diagram from the structure analysis, and you have capacity factor 0.9, so you can calculate ms section section moment. Once you know the MS, you can have MS equal to Fy and Ze. From MS, you can calculate Ze and Fy 300 as I mentioned. So you have Fy 300, and from that MS you have a value of 1191 your Ze value. So if you have 1191, let's go back in our one still tables. That is it coming? Okay. So 1191, you remember that one, right? So look at this plastic section modulus. We don't need to look at the elastic section modulus. Okay, I show you in the lectures. There was a good 15 minutes we spent for elastic section modulus and the plastic section modulus. So plastic section modulus we need to look. And what was that number? Magic number 11 was 1191. So let's look at that. That we need to have a 1191. Look at that, 1191, 1191. Okay, 1060 is down, then 1191. So we can't take it this one. We just go one step above, which is 1200 times 10 to the power 3 millimeter cube. So we can select this beam, which is 410 UB 59.7. So 410 UB, yes, 410 UB 49, what was that, 59.6 or something, 59.7. Okay, this they just write 60. So if you want to write 59.7 here, you can do that, and that has a ZX value of 1200, which is greater than this one. So we are okay, we are happy. There is one more condition though that you need to apply, that what would be your spacing. Like the spacing meaning, you have this beam, you have this UDL load, and then you have this loading here. They say that how far I should put this spacing, this lateral restraint, that will satisfy these conditions. That will satisfy these conditions, meaning that these conditions. Fully restrained. So if this L over Ry less than or equal to 80 plus 15 beta m, I'm happy that my beam will not have a lateral deflections. So I want to satisfy this condition. And by the way, beta m is here. Beta m on the next page, which is moment ratio, is minus 0.8 for transverse segment with transverse loading. So we were going to take this transverse loading one because we have UDL load. So we have minus 0.8. So we have minus 0.8. I show you that this equation. So L Ry we need to get it for our beam. Ry, which is radius of gyrations, 59.7 we selected, and Ry value would be here, and for that one is 39.7. So for that case, we have a 39.7. Bring this one across, 80, 50, 0.9, 300. You can have a spacing less than. If it is less than or equal to 1450, we are happy. We can have this one. So you can provide 1400 or 1430 or any values that you needed. So probably if you look at the beam, 16, so 600, so you can provide I think 1400, or you can provide 1500, because we don't want to have additional bracing. So 1500 quarter points you can have provide that bracing to that one. So if you put, let's say here, then